Okay, problem 1.33. Draw structures for the following molecules showing lone pairs. Okay, A, acrylonitrile. All right, so this molecular formula is given here, so it's C3H3N, C3H3N, and we're given another hint here. It says it contains a carbon-carbon double bond and a carbon-nitrogen triple bond. So this is actually, this isn't just a sort of totally fake scenario here just to teach you how to convert formulas to line bond structures. This is actually a common scenario in organic chemistry where you have instruments that will tell you things like there's a carbon-nitrogen triple bond. And there's also an instrument, a mass spectrometer, that will tell you the molecular formula, or essentially give you a list of possible molecular formulas. Infrared spectroscopy will tell you that there's a triple bond and maybe that there's a carbon-carbon double bond. And your job as an organic chemist is to deduce the molecular structure based on this information, the molecular formula and a few bits of information about what kind of bonds are in the molecules. So we can just look at this and figure out, based on valence rules, essentially, how these things might be put together. So there are 3 carbon atoms, and let's just number them 1, 2, and 3 here. So let's put these together in a way that makes sense. So let's just make a bond between carbon 2 here and carbon 1, and do that in a way that's a little bit neater here, or carbon 3. So if we just put the double bond here, and then the CN triple bond there, and make a bond between these 2 carbons, we have what looks like the beginning of a real structure here. We have our 3 carbons, our 1 nitrogen, we have our triple bond and our double bond, and now we just have to put in the hydrogens. And so that looks fairly straightforward. This carbon is bonded to 2 things. It's got a double bond to another carbon, so it has room for 2 more bonds, and let's just put in the 2 of the hydrogens there. Where's the other hydrogen? Well, it can't be here on this carbon because this carbon is already bonded to 4 things. It's got this triple bond and another single bond. The nitrogen here has 1, 2, 3 valence electrons. What if we put the hydrogen here? Let's see. We have 1, 2, 3, 4, 5. So this is okay in terms of the number of, sorry, we have 1, 2, 3, 4 electrons that nitrogen in this case owns, and so therefore it would have a positive charge and no lone pairs. And this is kind of looking forward to formal charge, but then this carbon is only bonded to 3 things, and we're out of hydrogens. We've already put the 3 hydrogens around, so this carbon is not a very happy carbon because it wants a full octet and it doesn't have a full octet. So we could say, okay, let's try a different approach here. Instead of putting the hydrogen there, let's put it on this carbon. So now this carbon has 4 bonds, this carbon has 4 bonds, this carbon has 4 bonds, and then this nitrogen, if we put a lone pair there, it has no formal charge, and it's got its 5 valence electrons. Essentially 3 bonds plus a lone pair makes 5. So this is the structure of acrylonitrile. Let's try the next one, ethyl methyl ether, C3H8O, C3H8O, contains an oxygen atom bonded to 2 carbons. So oxygen right here bonded to 2 carbons. So that means that there's 1 more carbon that we have to account for, and so we may as well just put it onto one of these carbons, since the oxygen only has 2 carbons that it's bonded to. And let's go ahead and fill in the lone pair here, and or the 2 lone pairs, and see if this works if we fill in the rest of the positions with hydrogen atoms. So 8, See if we can figure out a way to put 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. And the reason I only put 2 around this carbon is that it already has 2 bonds. So to make this carbon, give this carbon a full octet and 4 bonds, we would just put 2 hydrogens around this middle carbon. Okay, and I'll let you do the other two, C and D.